Let's revise the whole of turning points in AQA A-level physics. So this is part 2 and I'm going to link part 1 in the description of this video. We're going to start this video off with Newton's corpuscular theory of light. So Isaac Newton, who made monumental contributions to physics, actually suggested that light was indeed a particle, or the word that he actually used was a corpuscle. This is essentially kind of identical to what we call these days a photon. Now, Newton's theory was based on the laws of motion of the particles. For instance, a particle will keep on traveling in a straight line unless you act upon it with an external force. Now, diffraction wasn't really observed around that time. However, reflection and refraction were observed. So the way Newton explained something such as reflection was due to a force which, upon contact with, let's say, a mirror, would be acting on these corpuscles, and this would act to change their direction of travel, and then this would lead to what we now call reflection. Now, the other suggestion that Isaac Newton did was actually all about refraction. Notice something interesting about the reflection in this model. So the force is purely vertical, and because of this, this means that the vertical motion only is affected. So if the particle has two components of the velocity, so let's say that it's going down and then it's also going to the side, the horizontal component will remain exactly the same for all of these particles sort of before and after the reflection. All of these vectors are going to be the same, but it's the vertical component that will change. So let me just make a note here that the horizontal component remains constant or unchanged, and it is the vertical component that changes. It will actually have a complete change of the direction. So it's going down initially, and then it will be sort of like going up like so. So the way he explained that, which is also true in the wave theory of light, but let's say that we have a particle that goes from air. Let's say that it goes into something with a higher optic refractive index, so something like water, for instance. So when the particles go in, they actually start traveling faster, and because of that, they will change their direction as they enter the water, and then they're going to be bending towards the normal. So in this region, the speed of the corpuscles is higher. Well, there was also a wave theory which was published a few years after Newton had actually published his particle theory. So remember, corpuscles just means particles. Shall we just say that this here is a particle theory, and the rival theory was Huygens theory. I think in Dutch it's actually pronounced Huygens. However, yeah, let's stick to Huygens. So Huygens' principle relates every point on a wavefront. So let's say that we have a wavefront. Basically, we have a wave that, let's say that the wave is going in this way. His theory says that every point on a wavefront can be considered to be a point of a secondary wavelet that spreads out at the speed of the wave. Okay, well, what does that mean? I'm going to draw every point, but I'm going to draw out a few, and then all of these can be considered point sources. So this means that they're going to spread out like this, and this one here will spread out like this, and this one here will spread out like this, and so on and so forth, and so on and so forth. Now, All of these are going to have a point that is going to be tangential to their surface, and this will be the new wavefront. All of these should be nice sort of semicircles, by the way, but that's just a little bit more difficult to draw on a digital whiteboard. So we can think of this as the old wave front and this here as the new wave front. And it's through that mechanism that the wave is propagating this way at the speed of the wave. So these little wavelets are actually moving at the speed of the wave. Now, Huygen's theory could explain reflection and refraction using the idea of wavefronts. Well, I've demonstrated this using this diagram here. We have the wave front of a wave that is about to enter a optically more dense medium. At the boundary, when it meets the boundary, each individual point on that wavefront acts like a point source, and you can see that we have a line that is tangential to all of those circles that spread out, creating this new wavefront. Notice another key difference. In Huygen's theory, the light is traveling faster in the substance with less optical density. So let's just stick to the air and water example. So here the light is traveling faster, but let's say that this here is glass or water or whatever it is, something with a high refractive index, and then it slows down. So here it is slower. Now, you may be wondering, why is it that Newton's theory was actually preferred? Okay, well, this is another point on the specification. First of all, there was no experimental suggestion at the time that light was a wave. This will come with Thomas Young's experiment that we're going to be looking at in our next little chapter. So, Newton's theory was more popular because it explained the mystery of reflection and refraction using the more intuitive physics at the time of particles, because people are familiar with the idea of essentially particles that reflect, that bounce off things. Okay, Newton's theory though could not explain diffraction, simply because the equipment at the time meant that diffraction was impossible to demonstrate for light waves. Loads of people did also not want to disagree with Newton, as he was essentially the father of modern physics. He invented gravitation, he invented the whole field of optics, the Newton's laws of motion, which provide the basics of essentially the whole of physics. A crucial step in the debate on whether light is a wave or a particle was Thomas Young's double slit experiment. I actually have an entire 20-minute video on the mathematics behind it that you should check that out. If we're revising for turning points though, we're mostly going to be sticking to the more qualitative part of the specification. Okay, well, here's the setup. We have a lamp that goes through a filter so that it's more or less monochromatic, and then we need coherent light sources. So Thomas Young actually managed to produce a very narrow slit. So this here is a narrow slit, and this property of light is diffraction. So the way he did the experiment was to shine some bright light, and the diffraction would make the light appear as a single point source that will be diffracted, it will spread out, and it will go through two slits that will act as two independent sources which are coherent as well. As the light strikes the screen, what we actually observe, let's see if I can draw something, will be a series of bright and dark fringes. So whenever we have a bright fringe, we actually have constructive interference, and whenever we have a dark fringe, we have destructive interference. So this is a pure wave-like property that has been caused by wave superposition, and Huygen's theory was the correct one. Well, even though this experiment clearly proved that light had wave-like properties, it still wasn't widely accepted. Why is that? Well, Huygen's theory actually assumed that light was made out of longitudinal waves, but in a separate experiment we've already shown that light can be polarized, so it can't be both a longitudinal wave and exhibit polarization. But it couldn't also explain another phenomena such as double refraction and things like bright shadow edges, and there were a few things that it couldn't explain. However, in the coming years it became apparent that pretty much all of those experiments can be explained if light is a transverse wave, and pretty much straight after that Huygen's theory became the more widely accepted theory that light indeed has wave-like properties. Okay, now let's talk about the next big development in the study of light and the study of physics, and that was light as an electromagnetic wave. Now, the scientist that was fundamental to this was James Clerk Maxwell, a Scottish scientist who used the ideas of waves to unify electricity and magnetism into electromagnetism. He actually produced a set of the most beautiful equations that I've seen, known as Maxwell's equations. I have extensive videos of that if you're thinking about studying physics at university level. Now, a consequence of his theory was that there would be a transverse wave that is going to be radiating outward if there's a change in the electrical magnetic fields. In practice, how do you do a change? Well, if I have something like a negative particle, if I just kind of like oscillate that, move that up and down, then this should create a wave that is propagating outwards. And Maxwell predicted that there will be a spectrum of EM waves, all with different frequencies and wavelength, but crucially they will all be traveling at the same speed. And we need to know this equation, that the speed of propagation of those waves in a vacuum is given by 1 over the square root of mu naught multiplied by E naught. Now, E naught is just the permittivity of free space, and mu naught is the permeability of free space. They all have values that are given in the formula booklet. For instance, E naught is around 8.85 times 10 to the power of minus 12, and it's farads per meter, I think. And mu naught, on the other hand, in terms of pi, so it'll be 4 pi times 10 to the power of minus 7. Well, let's plug these into this formula, and what we're going to find is that we have 1 over the square root of 4 pi times 10 to the power of minus 7 multiplied by E naught, which is 8.85 times 10 to the power of minus 12. This whole thing is square rooted. If we put that into a calculator, we're going to get 2.9986 times 10 to the 8, which is about 3.0 times 10 to the power of 8 meters per second. Now, the main idea, and James Clerk Maxwell realized that the light must be a propagating transverse wave because the speed of light had already been measured independently, and there was a moment after he calculated that he was the only person in the world that knew that light was indeed an electromagnetic wave. So how was the speed of light actually known by Maxwell? Well, we need to have a look at Fizeau's measurement of the speed of light. So he carried out this particular experiment to try and measure the speed of light. There's a light beam right over here that strikes this mirror. The light beam is reflected, and then it passes through the gap of a rotating cog right between those two teeth. it strikes a mirror, and by the time that it comes back, as the cog is rotating, the light beam is then blocked. So using the frequency of the rotation, the time light took to travel to the mirror and back to the cog, you could actually calculate that time using the frequency. And with the known distance of travel, this whole distance, by the way, was kilometers. It was around 8 or 9 kilometers across this entire distance, because the speed of light is so large. But you could use that to calculate the speed of light. And Maxwell found that his calculated value for the speed of light was the same as the measured value by Fizeau, once again confirming that light is a transverse electromagnetic wave. So later on in the 19th century, Hertz produced and detected radio waves with the use of electric sparks. How did he actually do that? So radio waves were produced when high voltage caused sparks to jump between a gap of air. So the gap was just across here. Let's see if I can draw some sparks across it. So these things were charged. Basically, one of these was positive, one of these was negative, and then electricity would spark between them. Now, what he discovered was that this spark caused radio waves to be emitted from it. And as the radio waves were being emitted, even more interestingly, they induced a PD in a loop of wire which was right next to it. So this loop of wire had some current which was which started going through it, and this meant, well, something very, very important. Remember, induced EMF is proportional to the rate of change of magnetic flux. Therefore, this means that the radio waves had a magnetic component. Now, what eventually ended up breaking the wave theory of light was the photoelectric effect, and it all started with the ultraviolet catastrophe and this curve right here, which is the black body radiation curve. So all objects tend to emit EM radiation due to their temperature, and on the y-axis you actually have power or spectral radiance. There are different types of wave representing this, but typically you very often just have power on the y-axis against wavelength on the x-axis. Okay. So all objects tend to emit EM radiation, but at room temperature this tends to be in the infrared part. So if the temperature is quite low, the wavelength seems to be the peak wavelength seems to be quite high. Now, pure black bodies emit radiation in accordance with this curve, and this can be a little bit confusing, but a black body absorbs all wavelengths of EM radiation perfectly, but also because of that it can emit all wavelengths perfectly in accordance with this curve. Now, this curve could not be explained by classical, let me just add classical to my notes here, by classical wave theory. It predicted this strange peak across here, and this was essentially the curve that classical theory predicted, an infinitely high peak that was sort of happening somewhere around the ultraviolet region. This is not what the experiment showed. Well, this curve ended up being explained by Max Planck, the same guy as in Planck's constant, who suggested that EM waves can only be released in quanta, discrete packets of fixed energy, which turn out to be photons. He actually came up with this equation to try and fix this curve, realizing that the energy has to be proportional to the frequency, and this right here, h, is Planck's constant. There's two formulas for it, E is equal to hf and E is equal to hc over lambda. This idea was further built upon by Albert Einstein. He ended up winning the Nobel Prize for the photoelectric effect, saying that not only can EM waves be only released in discrete packets, but they can only exist, they can only be in discrete fixed packets of energy, which we now call photons. And now let's focus on Einstein's explanation of the photoelectric effect. So we have a photon, which I've represented by this kind of like squiggly line. Remember, it is not a wave though, it is a discrete packet of energy. And the energy of that photon gets transferred to an electron. Now, if the energy of the photon is greater than the work function, then this means that an electron will be emitted. If the energy of the photon is less than the work function, that means that an electron will not be emitted. There's also a one-to-one interaction only between a photon and an electron. What does that mean in practice? It means that if we use light of lower frequency, suddenly we can't just have, let's say, I don't know, 3, 4, 5, a million photons interacting with a single electron and still letting it escape. Because the energy actually appears in lumps and discrete packets of energy, this supports the particle nature of light. In practice, as I said, an electron is emitted, or whether an electron is emitted depends only on the frequency of the photon and not on the intensity. The equation that governs for it is that the maximum kinetic energy is equal to hf minus the work function. This is actually an equation for energy conservation. So the energy of a photon is split between the work function, typically given phi, and the rest is left as kinetic energy. This is Einstein's famous equation. Please note that the work function, which is this guy here, is the minimum amount of energy required for an electron to be released. Now, if this thing is at a minimum, this means that the kinetic energy will have to be at a maximum. What is the physical interpretation of this? Well, most of the electrons are not located near the surface and require more energy. Oops, this should say more, let's just add that. More energy than the work function, and essentially if the energy is higher, then this means that the kinetic energy will be lower because the energy of the photon has not changed. Overall though, Einstein's work was of fundamental importance. It won him the Nobel Prize and it showcased that light is made of particles of light, quanta of light, and began the birth of quantum mechanics. Okay, now light has some wave-like properties such as interference and diffraction. But also light has some particle properties or experiments that prove that essentially it's a particle in nature, and that is the photoelectric effect. Now, one of the most important works in the history of physics was Louis de Broglie's theory that particles have wave-like properties as well. He assumed that if light has both properties, then perhaps particles might do as well, and he calculated this jewel of a formula for the de Broglie wavelength, that lambda is equal to the Planck constant divided by the momentum of the particle. You can also think of it, and I think this is the way it's given in the formula booklet, that the momentum is equal to Planck's constant divided by lambda. Either way, they are inversely proportional, and this is really, really important. Now, this can actually be interpreted as a probability density wave, and then the amplitude of which is proportional to a square of the probability of finding a particle in a particular place is proportional to the amplitude squared. But importantly, the people thought about de Broglie's theory as a little bit of a theoretical curiosity, until they started doing crystallography. Now in crystallography, you fire off electrons to try and study the internal structure of a crystal. And what actually happens is that we observed diffraction, which was amazing. So the Broglie's theory was confirmed when, to the surprise, we fired off some electrons for a crystal, and then we saw a circular diffraction pattern. Now this gap size here between the concentric rings is actually proportional to the wavelength. If the distance increases, then the wavelength will increase as well. Now, something which appears quite often in questions, and it's really, really important, is this next bit here. So the small accelerating potential difference, and remember, we're talking typically about thermionic electrons by thermionic emission, so we can directly use sort of EV is equal to half mv squared if necessary. But the small accelerating PD means electrons with lower momentum. And the lower the momentum, the higher the wavelength, because they are inversely proportional. Wavelength is inversely proportional to momentum. The formula that we need to use to calculate this, if we're talking about the acceleration of electrons, is the following. And loads of questions appear for it. Lambda is equal to Planck's constant, which is around 6.63 times 10 to the power minus 34, divided by the square root of this expression, where m is the mass of the particle, e is the elementary charge, and v is the accelerating PD. So if the voltage is increased, this means that the momentum increases, which means that the wavelength decreases, and this means that this distance here in this figure will become smaller. So this is really, really important. The condition for diffraction is something that often appears in past paper questions, and remember, it's that the gap size or the size of the particle that is actually interacting with that with our particle that is diffracting, they need to be approximately equal to the de Broglie wavelength. Okay, typically we would calculate the de Broglie wavelength either with this equation or with lambda is equal to h over p, depending what we're given. Typically this when we are given the accelerating voltage. Okay, we need to also talk about an electron microscope, and then there are two varieties of it. In general though, we always have a stream of electrons is accelerated towards a positive potential, and they are both emitted via thermionic emission. So essentially we heat a filament up and some electrons eventually escape from that filament. To obtain useful resolution, our electron wavelength needs to be approximately equal to the diameter of an atom, which is, remember, 10 to the power of minus 10 meters, approximately speaking. Now, we tend to focus this stream of electrons onto a thin beam using what is known as a magnetic lens, or using a magnetic field to essentially influence the path of the electrons. There are two types of electron microscopes that we need to use. One of them is the TEM, the TEM1, the transmission electron microscope. I've got a very basic diagram here, but we have an electron gun here, and that electron gun kind of accelerates these electrons that go through the condenser first, and then they essentially get focused via the objective projector lens, and then finally end up producing an image on this fluorescent screen. We use a very thin sample, so let me just highlight some really important stuff. So a very thin specimen sample is actually used. The electrons that pass right through the middle are actually undeviated, but those towards the edges tend to be deviated by the magnetic field, and they tend to be sort of focused, more focused at a particular point until an image is actually obtained. So this tends to happen in the condenser lens, and the objective lens then forms an image of the sample. The projector then casts a second image onto the fluorescent screen. And this is one mechanism for the transmission electron microscope, which is very, very popular. We also have another one, which is the scanning tunneling microscope, or STM. This actually uses the principle of quantum mechanics or quantum tunneling in particular. For this one, we use a fine probe on the surface, and then a voltage is actually applied. The electrons have to overcome that Coulomb potential, and there is some probability that some electrons will cross from the sample to the tip of the instrument via a process known as quantum tunneling. If you think of the probability density distribution, let's imagine this here is the probability that an electron will go through. There's still some probability to go through a barrier, however quite a small one. If you're dealing with loads of electrons, it becomes more and more likely that you might see one or two of them. If an electron appears, then a current will be registered. Interestingly, if the probe moves over higher layer electrons, so let's say that we have the probe and we're kind of like moving this across here, then this will register a higher current. It's very important to know that the probe must be approximately 1 nanometer above the surface. And now time to have a look at one of my favorite experiments, and that is the Michelson-Morley experiment. And this will be the start of our study of special relativity. Now, before relativity's theory suggested that motion was actually absolute. What does that mean? That pretty much everything was in the background of something kind of similar to a substance in reference to the background, and this was known as the ether. Now, Michelson-Morley decided to test that using this experiment here. And here is the principle of the Michelson-Morley interferometer. The basic idea is to try and measure the speed of light in different directions. So according to classical physics, if light is going the same direction as Earth, then the two speeds would be added. So the effective speed of light will be given by the speed of light in a rest frame plus the speed of the Earth that's actually rotating. If it's the opposite, we would need to take them away. Now here is the principle. We have some monochromatic light which strikes a partial reflector. A partial reflector just simply means that it's a mirror that has been partially silvered. Now this splits this beam here into two. It splits it into this beam here and then into this beam here. Some of the light is reflected, it travels towards mirror 2, and some of it travels towards mirror 1. When the two beams actually come back, because they're reflected here and then here, they will actually interfere, and there's going to be some path difference that's going to be observed at that point. The idea here is that the whole apparatus is then rotated at 90 degrees, and this experiment is then repeated. Now, if the ether theory is correct, there should be a change in the phase difference between the two reflected beams as they're coming back and they're interfering with one another. However, no such shift was detected at all. In fact, absolute motion seemed to be impossible to detect, which was very, very hard to explain. The speed of light appeared to be exactly the same in every direction. And this invariance of the speed of light was of extreme significance to the development of special relativity. We also need to explain what an inertial frame of reference is. This comes up quite a lot in past paper questions, but in general, it's an inertial frame is just a frame in which Newton's first law is obeyed. Everything is moving at a constant velocity or at rest with absolutely no acceleration. If a frame is not an inertial one, there will be an acceleration of some sort, and special relativity does not really deal with those cases. Okay, well, Einstein developed the special relativity based all around the invariance of the speed of light. His two postulates of special relativity are its very foundation. Number one, the laws of physics are the same in every inertial frame of reference. The speed of light is invariant is our second postulate. Now this means something really bizarre. Imagine you have some sort of a spaceship, and then let's say that you just have some sort of a, I don't know, something like a torpedo. The torpedo is just a normal particle, and if you were to fire it off from the spaceship, the velocity of the torpedo would be the velocity of the torpedo itself with reference to the spaceship plus the velocity of the spaceship. Because the velocity of the spaceship was going at 500 meters per second, and now it's going, the torpedo is going at 1,000. If we're sitting right here in a stationary frame of reference, we're going to see that the torpedo in our frame of reference is moving at 1,500 meters per second with reference to the Earth. However, with reference to the spaceship, it's going to be moving at 500. Now, this is not how light works at all. If this spaceship switches on its headlights, according to the spaceship, the speed of light will be c, but also for us as well, in the frame of reference of the Earth, the speed of light will also be just c, where c is just our standard speed of light, 3.0 times 10 to the 8 meters per second. This is incredibly bizarre. The only way this happens is that if space and time are bent to accommodate the constant speed of light in every inertial frame of reference. Now, one way that this is accommodated is via time dilation, and the formula for time dilation is that t is equal to t naught, where this here is the time that an event has happened in a stationary frame of reference, and the other one here is in the frame of reference that is moving with respect to the stationary one at speed v. So this speed here, v, is the relative speed between the two frames of reference, and c here is the speed of light. Now this equation here actually means that time ticks slower, and there's many different experimental verifications of this. For instance, you've actually put two clocks, two very precise atomic clocks on planes, you fly them around the Earth for 48 hours, and you come back and they differ by the tiniest amount, exactly as predicted by Einstein's theory of relativity. Now, another one are muons, which are high energy particles which strike the surface of the Earth. Now, in the stationary lab frame of reference, they decay within a time of 2.2 times 10 to the power of minus 6 seconds. This is the lifetime of a muon in the lab. However, if a muon is moving at, this should say 99, let's just say 99% of the speed of light relative to the Earth, so it arrives via a cosmic ray, what is the relative lifetime to an observer on Earth? Well, the relative lifetime can easily be calculated using our equation, which we're going to use that as an example. We're going to use t is equal to t naught divided by the square root of 1 minus v squared over c squared. Our T naught in this case is just the lifetime as measured in a stationary frame, which is 2.2 times 10 power minus 6. And then we're going to be dividing that by V over C. If V is 99%, this is 0.99 C over C. We're going to square, and then we're going to take away and square root 1 minus 0.99 squared. Be aware that a really common mistake in exams here is just simply to forget this square. Now, this will lead us to a time of 15.6 times 10 to the power of minus 6. Now, this here is so much larger than 2.2 microseconds, and in fact experimentally proves time travel. The time slows down when you're traveling close to the speed of light with reference to a stationary frame. Time is not the only quantity which changes as we're traveling closer to the speed of light, or should I say, or as our velocity is increasing. Length contraction also happens. In fact, the length becomes smaller in the direction of travel as we are increasing the speed. And the formula for this is that L is equal to L naught, where L naught is the original length multiplied by this factor, the square root of 1 minus V squared over C squared. Now, an additional very important change is that mass in special relativity is represented with a different expression. In reality, we should really be talking about momentum and avoiding the term relativistic mass for a reason to the deeper understanding of special relativity, which if you study physics at university you understand, but just for the purposes of this video, because it's on the spec, I will talk about the new expression for mass, which is given as m naught over the square root of 1 minus v squared over c squared. This here is the famous Einstein energy equivalency, and that tells us that our formula for energy is very different in special relativity. If the standard half mv squared was true, if I keep increasing the speed, the energy will also keep increasing. But the mathematics of this expression tells me that this simply cannot be true. Now, why is that? Because if v is equal to the speed of light, then this will be 1 minus 1, which is going to be 1 minus 1, which is just 0. So it means that this whole expression is going to be undefined. Not only undefined, but as it gets closer and closer to infinity, borrowing an idea from calculus, it will essentially require more and more energy tending towards infinity as we're approaching the speed of light. And the curve for both the mass and the kinetic energy actually looks like this. Starts off pretty similar to half mv squared, but then it just tailors off and it reaches an asymptote. It reaches an asymptote as we are getting closer and closer towards C. The actual curves are just a little bit different. This bit is a little bit smoother, but it's kind of hard to draw on a digital whiteboard. Now, this experiment was tested experimentally by Bertozzi for the variation of the kinetic energy with speed, and in the exam you might be given some experimental results, for instance, and but the key idea is that he disproved that the formula that E is equal to a half mv squared is simply not true at high energies, and this a half mv squared is merely an approximation, and this is really crucial. He plotted actually a curve, and this curve turned out to be very similar for the kinetic energy against speed curve as predicted by Albert Einstein. And congratulations, we have now revised the whole of Turning Points, including part 1 hopefully, which I've left in the description of this video. But in the meantime, why don't you have a look at my ultimate physics exam hacks, which is just over here, that will help you get the maximum score out there.